Good morning. Really cool to have you all here. Hope your day is going well. We're going, oh, sorry. For what it's worth, it's one of those days for me too, man. The rain, the dreariness and stuff, I don't know. But it also makes me appreciate all of you being that much more and stuff like that. If I can help you with that, just let me know. Sorry. Today, we're going to continue, hopefully finish the exam prep review that we're doing, just going over different questions and stuff like that. And all this is to get you ready for Friday at 1:10, first midterm. And when you come to the midterm, we'll take that during the time. There won't be a problem set due or anything like that. Exam prep 1 is a worksheet that'll be due Friday at 1 o'clock. It's right after problem set 3 in the companion, or you can get it online. It's basically a single page, double-sided, questions given, answers given, show your work how you go from question to answer. Should be pretty cool. Empirical formula lab from last week, you'll turn in Friday. And then also after the exam, we'll do the percent potassium chlorate lab. This is kind of a fun lab, get to burn things, stuff like that. But because we're burning, please make sure you bring your safety goggles for that lab. Totally, you will need them, that'll be good. One final announcement is that today I do have office hours at both 10 a.m. and noon. At 11 o'clock, I'll go and get the lab ready for my Wednesday group. On Friday, my office hours will be a little bit different though, because we have a science division meeting. So on Friday, I'll be there at 8 o'clock, not 10 o'clock. 10 o'clock, I won't be there, but I will be there at noon again on Friday too. So sorry about this. This will happen a couple times in the term. I'll have to move my 10 o'clock office hour to 8 o'clock. That's just me. I mean, I love my team. So anyway, questions on any of that kind of jazz? Yeah.
What if your values for the empirical formula are like way off?
Cool. So if you think that your values are way off, a couple of things. First of all, in this lab, I'm more interested that you do the process and you go through the steps to do it. If your results are totally wonky, all right, and you totally get a wrong answer, this lab, it's not a big deal. Now the lab we're gonna do on Friday, I will grade you on your accuracy, like how close of a value you get. So that's a different kind of a lab. So that's one thing to realize. And second thing, if you'd like to put in the lab somewhere a statement as to why you think your results are weird and maybe what you think the compound should be, that's totally cool. So please realize that this lab, it's more about going through the process and getting you used to the things more than anything else. So include a statement. Other questions? All right. We left off, I just showed you this slide on Monday, but now we'll actually do it. So this is an empirical formula question where you're given percentages and then you can turn them into moles. Now the process for this problem, I would assume 100 grams total. 100 grams would be 46.67 grams of nitrogen, and you only have oxygen as your other part in there, so 100 minus that number would be grams of oxygen. You can then go grams of N and O to moles of N and O using the molar mass on the periodic table and compare them, and one of these answers will be the empirical formula. So I encourage you to check it out. After a few minutes, I'll wait and stuff, and then we'll talk about how to solve the actual answer.
Yeah, I want to make sure that's right. Click it, and that's good.
Yeah. So, click. See how it shifted up to now. And as long as you participate at least once, I'm sure you get credit for it. So next one. The check mark confirms, or should confirm that you made it to my 50 minutes, basically. Is everybody cool if I start talking about this problem? All right, so on a problem like this, there are several different ways to do it, but what I recommend, percentages first, find them both. So if there's only N and O, doesn't give you percent oxygen, but 100% minus this would be percent oxygen. Then you've got grams, if you assume 100 grams. So 46.67 grams of nitrogen, 50 whatever grams of oxygen, all right? Grams to moles would be the next step. So the 46.67 grams of nitrogen, I would divide by 14.01 or so grams of nitrogen per mole. That'll give you the moles of nitrogen. And then whatever the grams of oxygen is, divide that by about 16. Remember, if you just go to the 100th, it'll save you time. 99% of the time, that's totally cool. So you don't have to use, for example, 15.9994 unless you want to. 16.00 is awesome. Anyway, you'll then compare the moles, smaller on the bottom, bigger on the top. On this one, the moles come out to be almost the same, all right? They're each about 3.331, 3.333, and that's definitely close enough to be 1-to-1. So in this case, really, you can divide them both by the same. It's 1N to 1O. Your empirical formula should be just NO. Okay? So percentages to grams to moles, compare them. Good to go. Any questions on that? Now, here's a problem that's kind of like one we did in the copper chloride lab this week. In this problem, we've got zinc and oxygen, and we're taking 6.54 grams of zinc, adding it to some oxygen, and usually the gas is the excess. There's more of that than you need. But at the end of the day, then, you end up with 8.14 grams of this zinc oxide compound. So using this information, you can do the same thing we just did. You're going to find the empirical formula of this zinc oxide. Now, unlike the last problem where we had percentages, now you've got explicit grams of zinc, that number right there, which you can turn to moles. And 8.14 grams represents all of the zinc plus all of the oxygen in the compound. So 8.14 minus that will give you the grams of just the oxygen in the compound. You can turn them into moles. Compare the moles of O and the moles of zinc. See which one of these you get. Is everybody cool if I move on? Sweet. All right, so this grams right there is pure zinc, grams to moles using the molar mass in the periodic table will give you moles. Oxygen will be the difference between this number and this number. So 8.14 minus 6.54, so many grams of oxygen. And you can turn that into moles of oxygen by dividing by 16.00. If you do that, the moles of oxygen and the moles of zinc come out to be perfectly 1-to-1, at least with 3 sig figs. So that means that the moles of these are equal, and if you divide either one of them by 0.1, you'll get 1-to-1. Zinc oxide would be the formula ZnO. Right? And that kind of makes sense. Zinc is a fixed charge metal. It's the second step on the stairs. And the second step, zinc and cadmium, almost always positive 2. Silver's +1, aluminum, gallium, indium +3, but these two are +2. So if you're combining it with an oxygen, which is -2, hopefully they would be zinc to 1 oxygen. So, woohoo, go science. All right, glyceraldehyde has an empirical formula, CH2O. That's the smallest whole number representation of the molecule. Now, a separate experiment finds that the molar mass of the compound is about 90 grams per mole. You can use this information to find the molecular formula of glyceraldehyde. See if you can do that. Is everybody cool if I talk about this? Yes, sweet. So on a problem like this, you want to first find the empirical formula's molar mass. Now, I'm going to be real cheesy, honestly, about sig figs on these, and I'll tell you why in a little bit. So to just whole numbers, carbon's 12, hydrogen's 1, and there's 2 of them, and oxygen is 16. So this comes out to be, to very cheesy sig figs, 30 grams per mole. And you want to compare the empirical formula's molar mass to the molar mass of the whole compound. So the molar mass of the whole thing, 90.08, I just called it 90, all right? And I'm going to divide it now by my 30. And this ratio, why I can be cheesy with my sig figs, it's always a whole number if you've done it right, all right? So I'm not worrying about sig figs that much at all. And this is definitely a ratio of 3. Now this 3 is what you multiply the empirical formula by. So it's CH2O taken 3 times, all right? And this comes out to be C3H6O3. So you literally just multiply each one of those by 3 in order to get it. This part, you honestly can be pretty chill with sig figs, like I said, because the ratio will always be a whole number. Now in the empirical formula, you have to be a little bit more careful, because sometimes you'll get to like 1.5 to 1 ratios. So on those, I do worry about sig figs more. But these, as you can tell, no problem. Any questions? Okay, so this problem will combine lots of the things we've just done into one problem. And in this problem, you've got a compound with phosphorus and fluorine. And phosphorus and fluorine make several different combinations of compounds. But we know here that this compound is 75.41% fluorine, and so 100 minus that would be percent phosphorus. And we also know that the molar mass of the entire compound is about 252 grams per mole. You can use this information to find the molecular formula. There's a couple different ways to do it. See if you can figure out which one of those is correct. Is it? Yeah, that's fantastic. Sorry about that, I was thinking there for a second. Is everybody cool if I move on from this? All right. You will see a problem like this on Friday. All right. So of all the problems we've done so far, this one's a good one for practice. If you're knocking it out, awesome. If you're not, just focus on this kind between here and Friday. You still have time and stuff. If you really have a question like this and you don't have any idea what to do, I'm Prophet totally off on this one. One thing you could do, and I've had people do this on this problem, is literally like add 2 phosphorus and 2 fluorines together and see if you get 251.94. So like phosphorus is about 31, fluorine's about 19. So you could just add them through and only one of them, I think, will come up with this correct number. Now, that being said, a lot of problems, i.e. the short answer questions on the exam, won't have multiple choice questions. So I want to show you how this works. Now from there are actually 2 possibilities, all right? There's the math way, which is when you use percentages and stuff like that times molar mass. And if you did it that way, that's cool. But I'm gonna show you what I call the classic chemist way, because we're gonna go through some stuff coming up where this will be the method to use, i.e. the other way won't work. So in the classic chemist way, you would first assume 100 grams. So 75.41% would be 75.41 grams of fluorine, and 100 minus that number would be 26.59%, or that many grams of phosphorus. And then you turn them into moles. Again, to the 100th is almost always fine. So I would divide by 19.00, 30.97 for phosphorus, and you'll have the moles. And you can then compare the moles together to get the empirical formula. From the empirical formula, you want to figure out its molar mass, all right? And like we'll see in a little bit, the empirical formula is P1F5. So 1 phosphorus would be like 1 times 31, and 5 fluorines would be like 5 times 19. And again, on this part, you can be a little cheesy on the sig figs, because the ratio of the molar mass of everything, the 252 number, divided by the empirical formula's molar mass will be a whole number. So if you did this all, and it looks like people were taking care of business, P2F10 is the molecular formula. So now looking at these steps, here's the grams of fluorine to moles divided by the molar mass, grams of phosphorus to moles. This number is smaller than this number, so you want to go 3.69 divided by 0.97940. That comes out to be almost exactly 5, which is cool. And this divided by itself is just 1. So that's where the PF5 part came from. And then the empirical formula's molar mass would come, this is what I wrote right here. It's 1 phosphorus and 5 fluorines. So it comes out to be, with lots of sig figs, this number, about 126. But again, if you want to go 252 divided by 126, you're still going to get a ratio of 2. This ratio, always a whole number. This ratio up here may be fractions. So that's why up here, really critical, watch your sig figs, but here you can cheese out. So 2 empirical formula units means PF5 taken twice, P2F10. Any questions? Sweet. Okay. Real quickly, I just wanted to do 2 naming things. The first one is naming an acid. And the question is, which one of these is iodous acid? And you're welcome to put an answer in the iClicker if you want to, or I'll just tell you. If the acid, first of all, acids are acids because H is listed first. If there's no oxygen, it's hydroic acid. So that would be hydroiodic, in this case acid, which is weird. But hydro is not present there, so it's certainly not that one. Now for these right here, it's really helpful if you know what the most common one is, the ATE ending. And iodate is IO3 minus 1. And when you make it an acid, it becomes iodic acid. So HiO3 is iodic acid. And why that's supposedly helpful is that iodus, changing the ic acid to us acid, you take away 1 oxygen. So in this list, HiO2 would be iodous acid. If you add 1 more oxygen, it becomes periodic acid. If you take away an additional oxygen from iodus, it becomes hypoiodous acid. But this works for not only iodine, which I have up here, but also bromine and chlorine. And it does work for like nitric and nitrous acid. Now, nitric doesn't have a per nitric acid for reasons we'll see in chapter 22, but at least the relative oxygens is kind of cool. Any questions? Sweet. And then the other one, I just wanted to go in real fast too here, is finding the molar mass or the formula for a hydrated compound. And nickel 2 nitrate, nitrate is NO3 minus 1, and this means nickel plus 2. So nickel 2 nitrate by itself would be Ni parentheses NO3 parentheses 2. And then if you see this thing on the end, which I'm still getting questions on, hydrates are like we did in lab. It's a compound that water has attached itself to the main compound, and that's so that it's water. All right, water is attached to the compound. And hexa is 6, so you'd have 6 waters on top of the NiNO32. So when you're finding molar mass, make sure you include 6 waters. That would be 6 times 18 or so, and that comes out to be about 291 grams per mole. Cool. Any questions on that? Sweet. All right. So with that then, let's move on. We're done with studying for this thing. I am going to start chapter 4, part 1. Now, I want to make it very clear that this will not be part of the midterm coming up, but I can get started on it right away, which is a cool thing. Hope you do. Anyway, for chapter 3, doesn't really have its own chapter, which I know is really strange. Chapter 3 is part of Chapter 2, Part 1, Chapter 2, Part 2, Chapter 4, Part 1, Chapter 4, Part 2, which I know makes no sense, but that's kind of how we roll here. Chapter 3 is not organized in a way that I find super helpful, but it doesn't matter. what is important is that chapter 4, part 1, we're going to start looking at chemical reactions. And I've been battling a little bit how the periodic table is like my alphabet of letters, and you can take those letters and make words out of them, which in my chemical world would be elements to compounds. Well, now we're going to take the compounds and essentially make like sentences in chemistry. And chemistry is all about the chemical reaction, all right? This is an example of taking zinc and iodide and putting it together to make zinc iodide, ZnI2. Reactants are the chemicals to the left of the arrow in this chapter. Product or products are the chemicals to the right. So you can imagine this is what goes into the reaction and this is what goes out of the reaction. The diatomics are going to be pretty helpful in this section. So I just want to remind you, have no fear of ice, clear, blue. Those 7, HNFO, ICl, and Br, are the 7 diatomics. So when you have an element, one of those 7 by itself, you've got to list it as a pair. So that's why iodine is I2. Now zinc is not one of these, all right? And all the elements that aren't one of those 7 and are by themselves, you just write as single pieces, all right? Compounds can be any combination. You could have 3 iodines, 1 iodine, 2 iodines, like this one, whatever. But in the elements themselves, these are always by themselves as pairs, and these are always, when they're by themselves, just single atoms. Cool. So, without further ado, let's get cooking, because this is really kind of a chapter which is analogous to cooking. Now, my cooking skills vary a lot and stuff, and we don't need to go there. However, this is often really what my cooking experience comes out to. But I bring this up because really a chemical reaction is chemists cooking in the lab, all right? Now, you don't usually want to eat the chemistry cooking things and stuff that we make. So, but the reason why I bring this up is like, here's like making a cake, all right? And a cake has flour and eggs. This one has chocolate, some kind of oil. You mix these things together to make a cake, all right? The cake is a lot different than the pieces you put in, all right? Like you probably wouldn't want to take a big spoon of flour. That would be nasty. However, the cake, if you can tell, I really like cake. But anyway, I digress again. We're taking lots of different chemicals and making something quite different. And that's what we're going to do in chemistry. It's just, it's not as edible, shall we say. We're also really concerned with amounts. Now, in cooking, you've got to be aware of amounts too. But man, in chemistry, it's really important. All right, so we're going to pay attention to where the decimal points are and stuff like that. So. If you don't pay attention to stuff like that, that's when you end up with flames and explosions, or worse yet, and probably more likely, just nothing happens. And that's kind of sad too, because you waste all the chemicals. You have to buy flour and eggs and stuff at the store. You have to buy the chemicals that go into a chemical reaction too, and to just have them be wasted is kind of sad. So, woohoo! So let's get cooking. Now, in chemistry, unlike making wonderful cakes, this right here is more likely of a type of a reaction we do. And after we go through this section, you'll see that this is aluminum metal. It's elemental aluminum. It's reacting with oxygen gas, and it's making aluminum oxide. Now again, aluminum and oxygen are elements by themselves. But notice here, oxygen is one of the 7 diatomics, so it's listed as O2, all right, not just O. But aluminum is not one of these 7, so we'll just write it as Al. And we put this together to make aluminum oxide. Now, the little s and g there are pretty important to chemists. Those are called the states of matter. And the big numbers in front are also important. Those big numbers are called stoichiometric coefficients, and you'll never have to spell stoichiometric, so don't worry about that. So a chemical reaction, all right, which is kind of like a sentence, has a lot of information that it'll give the chemist. In this reaction, the S means solid, the G means gas. So we're adding aluminum, which is a metal, like aluminum cans or something. We're adding that to oxygen gas, which we're breathing right now. And at the end, we'll end up making aluminum oxide, which is also a solid. If you see an L, sometimes it's a cursive L, sometimes it's a regular L. That just means liquid, all right? So water would be a liquid. On the other hand, if you think your instructor needs more caffeine, which maybe I do, I'm not sure, but anyway, caffeine is dissolved in water and coffee. So caffeine, if I drink it in coffee, caffeine would be aqueous. It's a compound dissolved in another. If you take sugar and you put it in water, or salt for that matter, and put it in water and you stir it up, the sugar or the salt like goes away. It doesn't really go away, it just dissolves in the water. And so AQ means that it's dissolved in water. The stoichiometric coefficients are important too. Maybe if you have, I don't know, 1 Michael and 2 cups of coffee, you make happy instructor. Now that's a really dumb example, but you need usually I'll be honest, I need more than 1 cup to kind of jumpstart my heart, I guess. But anyway, these numbers are relative amounts. In cooking, it would be like so many cups with so many teaspoons or whatever kind of units you're using. In chemistry, these big numbers, these stoichiometric coefficients, tell you the mole ratios. So we're big time going to use those grams to moles conversions here. So this is saying really that you need 4 moles of aluminum to react with 3 moles of oxygen. And if you have those in those quantities, then you'll end up making 2 moles of aluminum oxide. So that's kind of cool. Arrows for this chapter will be one way only, left to right, all right? After this chapter, we'll see different kinds of arrows. But for this chapter, and that's what we see most of the time in chemistry, one-sided arrows are great. And again, to the left of the arrow will be the reactants, the part you put into the reaction, and the right side of the arrow will be the products, the pieces that come out of the reaction. Any questions on any of that? Here's a reaction where phosphorus and chlorine are combining to make phosphorus trichloride. Now, phosphorus is actually another weird element. You don't need to know this, but it actually is what they call a tetramer. It's 4 atoms at one time. We're not going to get real hung up on that, but I do want you to see once again, here's chlorine. Chlorine is a diatomic. So if you add chlorine by itself, it will be in pairs. Now, phosphorus trichloride, when all is said and done, comes out to be a liquid. This is the cursive version of L I was talking about earlier. And to make this all balanced, you're going to have to put a big 6 in front of there and a big 4 in front of there. Now, phosphorus trichloride is the product. We wouldn't write like P4Cl12, all right? Because we're making PCl3, not other kind of compounds. But you can absolutely change the big numbers in front, which is really important. A lot of energy is being released in this reaction. We're going to talk here in a couple chapters about the energy part of reactions as well. But for right now, we're just trying to get a sense for what reactants and products are about. Here's another example. This is iron and chlorine making iron 3 chloride. Now, iron 3 chloride is FeCl3. Chlorine, again, by itself, diatomic, so Cl2. Iron is not, have no fear of ice clear brew, so we would just write Fe right there. And then those stoichiometric coefficients to make the atoms that go in balance the atoms that come out are 2, 3, and 2. If you don't know if a chemical reaction has occurred or not, there's usually some kind of indicator that you can observe as a person watching the reaction. In this one, there's a lot of energy, like the iron actually gets kind of hot and crazy and stuff. But if you see like a solid form or you see gas coming off, and you definitely see some of that here, color changes and stuff, or you might even feel like the temperature, the container getting hot or sometimes cold. Those are all ways to tell that a reaction has occurred. And that's the chemist's job to see if a reaction is happening or not and how to control the reaction. This reaction, making aluminum oxide, is very, very exothermic, which is a term we'll use in a couple chapters, and that just means lots and lots of energy given off. You'll see like a firework, if you will, from this reaction when it's put together. This is like a picture of it. Now, this reaction up here has 2 meanings in chemistry, and I want to talk about both of them. First of all, on an atomic level, You can literally think about it as 4 aluminum atoms reacting with 3 O2s to make 2 Al2O3 molecules. And that's totally cool. But what we'll use most of the time in this chapter, as I babbled about earlier, is the mole equivalent. So 4 moles of aluminum react with 3 moles of O2 to make 2 moles of Al2O3. But if Clifford and I are philosophizing on what's happening in this reaction, we'll probably think about this version, like individual atoms coming together, electrons being exchanged. But if we're going to go to the lab and actually make aluminum oxide, that's when we'll start thinking about the moles. Because moles can be compared to something we can measure, the grams, we can get the grams out, stuff like that. Cool. The states of matter are always nice to include, but if you don't know the states of matter, it's not the end of the world. So we'll go through some examples later on stuff, and if you don't know that aluminum oxide's a solid, it's okay. So sometimes chemical reactions don't show the states of matter, and that's all right. But a good chemical reaction will always have a good balanced stoichiometry, and that's what we're going to hit here pretty hard. So.
Mercury 2 oxide breaks down or decomposes readily when heated. If we were to weigh the compound before heating and compare its mass to that of the mercury remaining after the reaction, it would seem that decomposition causes a change in the system's mass. The product mercury would weigh less than the reactant. In reality, the decomposition liberates the reactant's oxygen atoms as gaseous dioxygen O2. All matter present before the reaction still exists after it. The reaction obeys the law of conservation of matter.
In the old days, i.e. before the 1700s, basically, people were focused on making compounds, and they take very different materials and make kind of interesting kind of compounds, which is totally cool. But in the 1700s, people could start to think, well, what's happening here? How are these things being made? And one thing that was blowing their brains a little bit is how you could take a mercury oxide compound, heat it up, and the mass at the end was less than the mass that they started with. And they weren't sure like where the missing mass was going. And people talked about the ether and all kinds of different, phlosion is another term that was thrown around for a while. But anyway, what the current model predicts and what all this theory says is that, yeah, matter is just changed, all right? You're changing it to a different form. So before, these are the mercuries and these are the oxygens. They were combined down here as a solid. But you heat it up and the oxygens were essentially liberated, good old O2 once again, and then you end up with just mercury down there. So the process of figuring this out took a while, all right? And it wasn't until the 1700s/1800s this began to fall apart. This also leads to something that's really important in chemistry, because if you start with so many atoms, all right, you have to account for those atoms at the end of the day. Like you can't just like, if it was like you're using a broom and dusting or something, you can't just like throw it under the rug, all right? You have to know where everything is. And you can't just create things spontaneously either. You have to know where they're coming from. So a term we'll start using a lot is called, officially, the law of conservation of matter. And that just means that all the matter that goes in has to be accounted for on the way back out. Now, informally, that law is called law of mass action. And that falls off my tongue a little bit better for some reason, but they're both the same. And again, law of mass action / law of conservation of matter, all the matter that goes in has to be accounted for on the way back out. We unfortunately don't have magic. I'll make jokes about magic wands sometimes. Oh, I left my magic wand at home. But in our non-magic world, then we just account. Everything we start with has to be accounted for on the way back out. Questions? Cool. Lavoisier was one of the first people to kind of figure this out. Lavoisier was a French chemist. He was the one that's given the credit and stuff for that. And it basically, what Lavoisier and chemical equations comes down to is that the atoms that go in have to be accounted for on the way back out. You're not losing any mass, you're not gaining any mass, all right? So in a balanced chemical equation, the mass that you start with is the mass that you end up with. Lavoisier was beheaded in the French Revolution. Politics and chemistry don't always mix together. Yep.
Tell me you have good news.
The universe never lets anything go to waste, or so said Lavoisier.
About conservation of mass. Yes.
In chemical reactions, mass is neither created nor destroyed.
So this is a cheesy little clip that I'd forgotten I even put in from Star Trek Discovery. You don't have to like Star Trek to do well, but anyway, they actually mentioned conservation of mass. Yeah. We'll talk about on the quantum level how there's some flexibility there, but that's for Chem 222, not for right now.
When pieces of aluminum foil are placed in a beaker containing bromine, a violent reaction occurs. The elements react to produce aluminum bromide, which consists of 2 aluminum atoms for every 6 bromine atoms. It is visible as a white powder deposited on the beaker.
Cool. In this reaction, the brown gas is bromine. Bromine is technically a liquid at room temperature, but when you react it, so much energy is given off that a lot of it ends up kind of like that brown stuff right there. And the actual aluminum bromide, which is a dimer, by the way, you don't need to worry about that, is this white stuff right here. It's the very top of it. So we put some raw aluminum in, we added a bunch of liquid bromine, a lot of energy was released, so you can see a lot of bromine vapor escape. But at the end of the day, then you've got Al2Br6, this compound. Now this is a graphic description of what's happening on the atomic level. The kind of gold atoms are aluminums. So you can see that these are the reactants, what you put in. This is the product that's coming out. And if you look carefully, 2 gold and 2 gold atoms, so the atoms that go in equal the atoms coming out. And bromine, the dimer, 1, 2, 3, 4, 5, 6 bromines, and there's a total of 6 bromines right there. So if you look at this carefully then, there are 1, 2 aluminums, so we put a 2 right there. Now bromine comes in pairs, all right? So there's 6 atoms of bromine, but we think about bromine as the dimer. That's what the 7 diatomics are all about. So there's 1, 2, 3 dimers. You put a 3 right there. And there's only 1 of these. And so by default, chemists don't put 1 in for a chemical reaction. You would just write this as 2Al plus 3Br2, making 1 Al2Br6. So this is the first reaction. It's balanced reactions go in, equal products coming out. All the atoms are the same. Notice that the moles are not the same. 2 moles of aluminum and 3 moles of bromine are not equal to 1 mole Al2Br6. So the atoms are the same, but the moles are different. We'll talk about this more on Friday. Have a wonderful day. See you soon.